So, okay, so these are the are there 5 different types? 1, 2, 3, like 4 different types of polars that you'll probably see. If they give you any other one, then they'll give you the graph for you. But one of these, they won't give you the graphs for because you're expected to like know how to solve it. So remember, these limasols are all of the form a plus or minus b sine theta and a plus or minus b cosine theta. And those you just want to graph the 4 points on the axes, and then they'll tell you what it should look like. Okay. If you have 2 points that are on one side of an axis, then you know you have a loop. But if your points are on either on all 4 axes or at the origin, then you don't have a loop. For roses, the even number of petals, you want to double that amount, and the period of that is 2 pi. For odd number of petals, then you would have the same number of petals, but your period is only pi because it starts repeating over itself. Circles are just a cosine theta or a sine theta. They kind of look like roses, but with only 1 petal. And then lemniscates are r squared equals a squared sine 2 theta, right? Okay, well, so now we're going to do area of polars. So, do you remember the area of a sector? So if I have a circle, oops, and I want to find the area of just like one slice of this circle, right? Then I take the full circle, right? I don't know why I wrote a theta, it's a full circle. Full circle. What's the area of a full circle? Pi r squared, right? And then I take the full circle and I multiply it by the percentage of the slice, right? Okay, so the percentage of the slice is, if this is theta, right, then the percentage of my slice will be theta divided by 360 or 2 pi, right? So that's how you get the area of just like one slice of a circle, right? Pi r squared times theta over 2 pi. And then if we simplify, the pi's cancel, and then you just get 1/2 r squared times your theta. And so that's the area of a sector. Got it? Okay, so that's one little pie slice. So what we do in polars, you know how when we were doing calculating area for rectangular graphs, we drew little rectangles, right? And then added them all up, a Riemann sum, right? Okay, and then we added up all of these little rectangles. That's why it's called rectangular form. So, and then it was f of x, the height of the rectangle, times the width of each rectangle, your dx, right? And then we wanted the dx to go to infinity. We wanted an infinite amount of them. So then, and then we added them all up together and it ended up being the integral, right? Okay, we do the same exact thing for sectors. For polars, is you find the area of one sector and then you add it to the area of another sector. The smaller your theta, the more accurate your area will be, right? So at the end, after you compute it all and you add up all the areas of each sector, you get the area of the full polar. So this is not a stack to find the area, this is kind of like a fan out. Think of it as like a fan that you're fanning out. So the area of a sector we said is 1/2 r squared, and then our theta, just like our x dx here, was the thing that we wanted to get super small. Our theta is the thing that we want to get super, super small, right? The smaller it is, the more accurate your area. So it's going to be d theta, okay? And then we add up all of the pieces. So this is the area of a polar, if you want to calculate area of a polar. So it's 1/2 r squared d theta. That's basically what this whole page is explaining, but it's all down here. They usually put the 1/2 on the outside, but you can leave it on the inside if you forget it. Okay? Cool. Now, let's try it. So, here's the formula here. Our first question says, find the area bounded by the graph of r equals 2 plus 2 sine theta. So first, this is what is this? Yeah, it is a cardioid, but if you don't really know, just a lemniscate is good. So for lemniscates, you do theta and r, right? And if theta is 0, what is my r? 2. Okay, so 0, 2. So at 0 degree or 0 radians, we go out 2. So be careful because you're gonna try to graph like over 0 up 2, because you'll go back and forth from rectangular to polar, but just stay in polar. At pi over 2, my r is 4. At pi, my r is at 3 pi over 2, my r is 0, right? So when it hits the origin like that, you know it's a cardioid. A cardioid is a type of lemniscate. So, all right, and then you graph. So remember, you start at 0, like, so this is your starting point right here. And then we go around, try to draw it kind of fat. You don't like, fatter is nicer. The skinny ones don't look as good. Okay, so here's what we're doing visually. What is it? 2 plus 2 sine theta? Is that right? Okay, this one only does it in degrees, but basically, here's your cardioid. Here you are at 0 degrees. My A is 0 degrees right here. And so when we calculate area, this is how it's actually going. So when we're doing this integral from A to B with the 1/2 r squared, it looks like this. So as you go along, it's calculating area like this. Okay? So if I stopped here, then it would calculate only that area, the fan of that area. Okay? So if I go all the way to pi over 2, it would only calculate, since it's starting at 0, it would only calculate area from there to there. So I'm only getting like this little piece. I'm missing the little blood part right there. Then you go, keep going, and to pi, you get almost the whole thing. But remember, if you go 0 to pi, it's not like you're getting half of it, you're getting the chunky end of it. And then to 270, you're getting that much. And then to all the way to 360, you calculate that much. Okay? So it follows. That's why it's important. That's why I told the pre-calc teachers last year to kind of restrict your intervals so that you got used to like the way that the graph goes. Because if you don't know the motion, then it's hard for you to visualize like how it's calculating area. Okay, got it? All right, so we are going to integrate. Where's my pen? So since we want to go and draw on your paper, like here, it's like I kind of do this so you know how it's calculating. So it's not going top to bottom, it's going like from the origin out to every single point. Okay, so we have the 1/2 on the outside, and then integral from, we want the whole thing, so we're going to go 0 to 2 pi of r squared, so 2 plus 2 sine theta squared d theta. Okay, I'm going to show you how to solve these by hand. We'll have to expand this. So 2 squared is 4. 2 times 2 sine 2 theta. 2 times 2 sine theta times 2 is, okay, hold on. Plus 2 sine theta quantity squared, 4 sine squared theta, d theta. Okay. 2 identities from pre-calc that will help you is I'm going to write it here and then we'll transfer it over. The cosine 2 theta identity can be rewritten in 3 different ways. The cosine squared minus sine squared, but this is the other way and this is the other way. If I solve for cosine squared here, then I'll get cosine of 2 theta plus 1 all divided by 2, right? Okay. And then if I solve for sine squared theta here, then I'll get cosine of 2 theta plus or minus 1 all divided by negative 2. Maybe we'll flip it. We'll make this 1 minus cosine 2 theta divided by 2. And we'll flip this one too on our notes here so that we have it. So cosine of 2 theta, there's 2 options for you. Oh no. Yes. Is 1 plus cosine 2 theta all over 2. Okay, so I put the 1 in the front just so that it's the same pattern. And this one is 1 minus cosine 2 theta over 2. So sometimes I remember it as, hey, if it's cosine, then it stays positive, but if it's sine, it switches to negative. Okay, but it's the same formula. Okay, we can put this in for that now. So this part right here can be replaced. Plus 8 sine theta plus, and I'm actually going to put this in, but I'm just going to make it 2. Okay, because all I did was I canceled out this 4 with the denominator here and then made it a 2. In front. Makes it a little bit nicer for us. Okay. Do you want to simplify some more or no?
No.
Well, we're going to have to integrate, so we either simplify now or we simplify later. Okay, so we have 4, this 4, and this 2 is 6 plus 8 sine theta plus, and then this 2 gets distributed to that one, so, oh, we'll just make it a minus.
We're at 6.
1 plus 2.
The yellows. Okay, now we integrate. 6 theta plus, yep, minus 8 cosine theta minus sine theta, sine 2 theta from 0 to 2 pi. We gotta plug in both, because remember, sometimes cosine of 0 and sine of 0, cosine of 0 doesn't equal 0. So we have 1/2, 6 times 2 pi is 12 pi, minus 8, and then sine of 4 pi is 0, minus 0 plugged in is 0 minus 8, and then sine of 0 is 0. Okay. So, our answer?
6
That was pretty nice. Yeah, it is a very clean answer. Let's go back to our thing. Is 18.8496 pi? Yes, it is. Did you get 12 pi?
Yeah. No,
Or 16 pi?
16 pi, what?
I don't know.
No, 6 pi.
Oh, 6 pi.
Yeah, 6 times 3 is
Yeah. Okay. Feel good? No? Alright, now let's do petals. So, how do you graph roses? Well, since we want the area of one petal, then we should figure out where the petal is first, right? So there's 2. Yeah, but how do we do that all the time for every rows that we have? Well, we know, hold on. We know that a petal will begin and end at the origin, right? Yes? Okay. So if we set this equal to 0, then we should be able to figure out of the beginning and the end of our petal. So we'll divide by 2. So 0 equals sine 3 theta. When is sine 0? 0, comma, pi. We don't really need any more, right? We need the beginning and end of one of them. And then we divide by 3. So divide by 3, divide by 3. So we know our petal begins at 0 and ends at pi over 3. Okay? There's another way you could do it. You could set, so this is finding beginning / end of petal. Okay, there's another way you could do it. You could do it where you set it equal to 2. Okay, because you know the pedal's length is 2. So if I set it equal to 2, I can figure out exactly where the pedal will be. So if this is 1 equals sine 3 theta, then sine is 1 at pi over 2 equals, oops, sorry. Oh my God. Sorry, guys. So theta equals pi over 6. So that's where the pedal, one of the pedals will be. But you can also find it. So this is pedal location. If you like that better, you can do it that way. So you know it's going to hit out at pi over 6, which is right here. Out 2 at pi over 6. So it's going to go out and then come back in at pi over 6. But if you have the 0 to pi over 3, you know a pedal is going to happen in between them. So.
Is there a reason you want to use pedal location?
Nope, it's up to you. Sometimes, oh, there is. Sometimes you, it'll tell you exactly where the pedal lies.
How would you use pedal location for that?
No, I'm just saying to draw the actual pedal.
Oh, to just draw it?
To draw it. Okay, we don't need all 3, but if you wanted to see all 3 here, we'll change this. What is the? I know. You gotta give me a minute, Albert. Can't. It's hard to work and do this at the same time. I'm a trained person, but it's very fast. Okay, so see how this interval is 0 to pi? Because if I went 0 to 2 pi, it would overlap twice. So that's important for you to know. You can only go 0 to pi. So as I calculate area, the actual pedal starts at 0 here, and then it ends back at pi over 3. But the next pedal, because polars don't ever have sharp points. So the next point will be, it's going to come down here. So it's graphing like this. If you look at the area, this is how the area is going to go. So 0 to 30, or pi over 3, 0 to 60 is going to be like that, right? And then if I calculate more, that's up to 120. And then that's up to 180, okay? The red ones is because your R is negative for that, because at pi over 2 it ends up down here. So that's what happens when you go. And then if you went all the way to 360, you would be overlapping again. So you'd be like doubling it too much, okay? So we only want to go 0 to 60 degrees, or pi over 3 radians. All right, but actually, guys, you could go 0 to 30, right? And then take out the 1/2 in the front, because it doubles it. You're staring at me like,
Well, that makes sense. Why
yeah, because
do
then you
go
don't
back
forget
to
the
that?
1/2.
That just makes things complicated.
Well, it's up to you. It depends on what complicated is to you. If you forget the 1/2 often, then it's better to just multiply it by 2, only find half of it, and get rid of it. But if you think it's more complicated to think of halfway, then just go 1/2 integral 0 to pi over 3. Which one do you want? Yes.
Normal way.
Okay, 0 to pi over 3 with a 1/2. And then our R is 2 sine 3 theta, all squared. By the way, guys, when you go back to rectangular, when you're finding area, don't square it. Because you're going to get used to squaring things to find area for polars. And then when you go back to rectangular, you don't need to square them.
How do the AP exam is?
So, polars.
Yeah.
They'll definitely have a couple multiple choice questions on polars. And then it alternates. Well, they'll either give you a polars or a parametric free response on the AP exam.
Which one?
Yeah, and it's one or the other. So last year they gave a parametrics. So I'm thinking this year they'll give you a polars. But it's not like, it doesn't go like year by year. 6. There's 6 free responses, and 2.5 of them are AB concepts, and then the rest are BC concepts. You will always have a sequences in series free response, and it will always be question number 6. Okay, I'm gonna pull this 4 out too. Make it easier. Nah, actually, I'll leave it in.
What'd you say?
Because I'm going to replace sine squared 3 theta with one of those, with this identity in green over there. But I've got to make this cosine of 6 theta. Okay? And then the 4 and the 2 I'll cancel now, and then I'll bring the 2 out. Okay, so that makes it just integral 0 to pi over 3. Are you with me? Okay. Now the integral of 1 is theta, and the integral of cosine of 6 theta is negative 1/6 sine 6 theta. But doesn't it stay the same sign?
Right. Yeah. What happened in the 4 times? Got rid of it.
Well, okay. 4 and this 2 cancel, and it
Oh,
becomes a
you
2,
cancel with
and then I
the
pulled it out with a 1/2. Yeah. Okay, so we got pi over 3. 1/6, or sine of 6 pi over 3, that's sine of 2 pi, right? So that's 0. And then 0 plugged in is just 0, so it's just pi over 3.
Because you found that.
Because, like, 0 is where the pedal started, right? And pi over 3 was where the pedal ended. Yeah, and it's 1 pedal. So if you wanted all 3 pedals, you just multiply it by 3. So all 3 pedals, your area would be
So if you
pi.
wanted all the pedals, you just have to do it from 0 to pi, because that'd be the whole period. Give it to pi.
I'm going to try it. Sometimes it works, and other times it doesn't. Yeah, it does.
What?
You could go 0 to pi.
Always, if you want all the pedals.
Yeah, but you have to be careful about even number, odd number of pedals, and
No, but like
keeping the
it's-
period.
Like if it was odd, then you would always go from 0 to pi from the pedals.
Mm-hmm.
And 0 to 2 pi.
Mm-hmm. Okay. All right. Why don't you try this one and tell me what you get?
Can't you just like divide the period by whatever the pedals for each individual pedals period?
I'll try for the next one. I don't want to make a generalization. It's like almost better to just find where they are. So I feel like sometimes it works for me and sometimes it doesn't. So this is good to practice finding, you know, locations and stuff anyways. This is parametric is
Oh,
Yeah.
parametrics.
Not actually, I know.
parametric is degree.
That would be
No, because Mr. Wood.
Yeah, she was at the
Oh,
unit.
I was like, this is what I do with the paramedic. This guy was like, what? She was secret. Yeah, you knew. Because it was like when I said, yeah. She was out with that too. She was out the first day, which was like converting.
Yeah, she actually made it, but we didn't pay attention.
Then that's on you.
I don't know.
Well, like, also, it was just loud
that we couldn't
anyways.
ask her.
Like, nobody was paying attention, so, like, even if you wanted to pay attention, you couldn't.
You can go home and watch them.
Now, that's because like all of our questions.
Do you think I have that kind of motivation?
Sorry.
At least last year.
This guy. Oh my god, I still didn't understand how a paramedic. I thought that like the X value was still just an X value. Oh, but I don't think it was like a distance.
Oh, but it doesn't.
What's up, Anjali?
Oh, never mind. I just realized it's 0. It's not zero. It's 0. You have to start at 5.
It's 0.
Oh, yeah. If you were at 0, then your pedal is actually out
Yeah.
that much, yeah. So, guys, did you go from pi over 4 to 3 pi over 4? That's totally fine, but your pedal is actually on the bottom. It doesn't matter, but your R's are negative. But since you square them anyways, it doesn't matter.
But I didn't know.
Like the R values are negative,
Right.
so the pedal's actually on the bottom.
Right.
It doesn't matter. You're still calculating area because you're going to square it and the area will become positive.
Okay.
But just so that you know. Because the pedal actually, like it at 0 degrees, this is the motion.
Yeah.
It's at 0 degrees, it starts there, and then this is how it calculates as it goes
I
around.
got that. I'm just trying to figure out what you mean by like, oh, so the R value is negative.
Yeah, because at pi over 2, your R values are negative up here, so you go down. Yeah.
Right. Okay.
Not a big deal, but just something you should know. Okay. Yes.
So sad. I just like do that like slow thing. That's really satisfying.
And of course, you know the person who chooses the
Oops.
No, but seeing it get graphed on your calculator is just way cooler.
That's so funny.
Oh yeah, as it goes on its own. Add in a 2.
Success.
2 plus.
We're not doing any notes, are we?
No. If you do, they'll give you like the graph of it.
That's weird.
Oh.
Wait, go back more.
You see the swirly thing? Oh, not
Okay. Anyways, let's go to 1 minus 2 sine theta. Just a swirl?
Yeah, like drag it like the shades.
Oh, I don't have that on here. You can graph it on your.
You just make it a variable and then it automatically makes the slide.
We don't have time. We have to do this. Okay. This one is this is a limaçon because it's 1 and it has a plus or a minus. So we have R and theta. Oh, I like my thetas here. I don't know about you. Okay. Theta is 0. R is 1. At theta equals pi over 2, R is so we're down here. At theta equals pi, R is, and at theta equals 3 pi over 2, R is 3. So see how you have 2 points on one side of the axis? Then you know that you've got a loop to draw. So we're going, we cross through the intersection. We go up around, cross through, in, up, over, down, connect, up. Okay. Got it? Okay, we just want the inner loop. So just this little part. How do we find where the inner part begins and ends? Yes. Set it equal to 0 because it's going to start inside the loop when it hits 0 and it's going to exit when it also equals 0. Okay, so 2 sine theta equals 1. Sine theta equals 1/2. Theta equals and 5 pi over 6. Let's make sure we did it right. So if we go to our image, what was it? 1 minus 2? Okay. So we start at pi over 6. And then we end at, 5 pi over 6. Yeah, pretty good, right? So that finds our inner loop. Let's do it. 1/2. If you want, you could go from pi over 6 to pi over 2 and then double it. If you want to get fancy.
No, it's fake.
Okay, fine.
Oh.
Gotta use that identity again. One squared, 1. 1. This is make sure it's good. Then we replace this one with 1 minus cosine 2 theta over 2. That goes in for that. So, Which one? Oh yeah, thanks. Hey Andy, you want to learn this before you learn this? Like a stray?
Bye, Miss Malay.
Bye. Okay. 5 pi over 2 minus pi over 2 is 4 pi over 2. Should we simplify this?
Can we just leave it
No.
like that?
We got time.
You want to leave it? We can leave it.
Simplify it.
What?
I kind of want.
You simplify it.
I did. You're right. I didn't realize we didn't have.
Wait, when it's sine 2 theta,
If I had to.
never mind.
The answer is 0.543.
Yeah, I would've gotten that.
Wait, when you plug in 5 pi over 6 into sine 2 theta, then doesn't it equal 1? Wait, no, that's what I said. Never mind.
It's 5 pi over 3 then, right?
Yeah, no, I got it.
Okay. All right. Are we ready to move on? Oh man. Where is my notes? It disappeared. Uh-oh. It stopped working. Yes. What? Yes, of course. I've run into technical difficulties, guys. Now. It's taking a while. What page were we on?
In the loops. What does it be?
Yeah.
There's no value. There's no nothing.
There is.
Isn't that just not part of it? Oh wait, we're making a circle with
Okay. No, this is the same graph.
just subtracting from like a R value
Okay. Now, guys, listen up.
Yes.
Aaron, is it that bad? It's kind of bad. Is it that bad? Yeah. Yes, Anjali.
Wait, for this one, could you just do 0 to pi over 6 and then 5 pi over 6 to 2 pi and like add some intervals?
Yes, but an easier, even easier way.
Hold on, what does it mean area in between the loops?
Area in between the loops. Okay, let me go back to this. It means this.
It means the area that isn't the loop.
This like donut.
Okay.
Okay, so see how we already figured out this little inside part? Are you with me?
Yes.
We already figured out this inside part. So, in order to do area in between them, then we're gonna go, but be very careful because here's what we're gonna do. We're gonna integrate. There's multiple ways you could do it. But my way, the way I like the best, is to integrate from 0, and then calculate this area. Keep going, calculate that area, keep going, keep going, keep going, keep going. And go from 0 all the way to 2 pi. And then I'm gonna have to subtract this little teardrop twice. Because watch as we integrate from 0 to 2 pi. So as I go around, see how I calculate this area, right? And then when I go around again, I'm doubling up on that area. So we're gonna take off, there's like 2 layers. We'll take off the top layer and then take off the inner circle from it too. Okay, so you can do it that way. The other way is to integrate. Some people like to start their point at where the thing starts and go, I'm sorry, where was it, at 150, right? No, I think it was at 150, right? Okay, they start from like the end of the loop, and then they go to here and they calculate that area, double it, and then take out the inside. But the best go 0 to 2 pi and then take out the layer twice, right? Scoop out 2 layers. Okay. Yes.
But if you're taking out the middle layer twice, isn't that gonna just be like sort of the same as adding it?
No.
No, you subtract
Okay,
2
but like-
times the area.
Because
It's not
negative-
a double negative.
Okay. I mean, because it's negative area. and then-
No, it's never negative area because when you are square, like I get it, it's a negative r. However, when you square it, it's always positive.
Well, why do you take it out twice?
Because as you look, as it's graphed, notice. So if I go 0 to pi, it's calculating it all of that area, including the red. If I go to 2 pi, I have now made 2 layers
Okay, but why do you subtract it twice and not once?
because I've made 2 layers. Do you see how this?
Yeah, I see how like. It
And do you
goes
see that
over.
underneath the red?
Yeah,
It's
I
not
do. But I
right.
still
So
don't
that's
get
2
why-
layers.
But yeah, it's 2 layers. But why do you subtract it twice instead of subtracting the layer once?
Because I don't want the loop at all. I've got to take it out completely.
Oh, okay. Alright, I missed that. part.
Okay.
I thought we were calculating the whole area.
Yeah, if we wanted just area bounded by the polar, then we would just subtract it once, like all the area inside. But we just want in between the 2 loops, so we've got to take it out twice. Okay. All right. So we're gonna do the same thing here. It's not gonna be too bad though. Because we've already figured out what the integral is. Okay, that one's not too bad, right? So this is just 3 pi. So the whole thing's 3 pi. And then we just subtract. Oh, we should have simplified.
No, we just make the whole thing.
I would just make that whole thing equal to A
I
and
got
then just say
pi
that pi
minus
minus
3
A.
over 2.
You got what?
I got for the simplification of the first one pi minus 3 root 3 over 2. Yeah.
Okay, we'll just. This is by it, Dean.
Oh, okay.
Verified by Gray. Alright, so I think we might have.
Oh, okay.
Oh, she's just great.
Checked.
I think you checked. You checked.
Checked by Greg.
Should it be minus 2?
Yeah, it should be. 2. Okay. Cool.
Wait, how'd we get that?
Oh, that was from our. We did it here. It's the same problem.
Oh, okay.
That's why I didn't have to spend all this time integrating because we already integrated it. Okay. Ready for the last one? Okay, 3 sine theta. That is a circle. Up 3. Make a circle. My circle's so nice. I am. Okay. And the next one is 2 minus sine theta. So let's plug in 0. That's 2. Plug in. That's this. 3 sine theta is a circle.
I get that. I said I was
What?
How'd you get it?
So nice.
Yeah.
Oh, I use the circle tool. Fine. You got me. 1, 2, 3. Okay.
I'm not a fan.
You know, 3, 4.
It's a dimple 3 or something.
It's like Valentine's Day and we're doing hearts, guys. It's Valentine's month and we're doing hearts.
Today's half hour.
Isn't today Singles Day?
What?
Isn't today Singles Day?
Is it?
Yeah, I forget.
It's half hour.
Well, that's why we found the area in between the loops because
Half hour
we're missing
That's
something
why they have to
inside.
do it. They have to get rid of all the chocolates.
But this loop will fill it.
Oh, sweet.
No, I know. That's why you have to make it deep.
Really deep, right? Okay. Now, we've got the area inside r equals sine pi theta and outside, inside my circle, outside my green. That's this area. Okay, I don't have a fancy thing where I can do 2 graphs at once, so you're just gonna have to imagine. This is the first year I've been able to like show a good visual. So other classes have lasted
Really good.
till now. You will survive.
That's just the last one. That's exclusive to one.
Okay. So, draw a line from your origin out to the 2 intersection points. Okay? So, since I want this red section, first I need to find the 2 intersections. So how do I do that? Set them equal to each other. For sine theta equals 2. Oops. When is sine 1/2? Okay, cool. Now what? So here's what we're gonna do. We have our two intersection points. What's our circle? 3? 3 sine theta? Okay, so we're gonna go from, what is it? Pi over 6 to 5 pi over 6. Okay, so we're gonna find that. Do you see how it only calculates like the fan part here? Okay, so we're gonna go there, and then we're gonna take away that other stuff. All right, so that is 1/2 integral pi over 6 to 5 pi over 6 of circle squared. Okay, so that's that part that we found. And then we're gonna go, what's the other equation, guys?
2 minus sine theta.
Okay, then we're gonna go same place to same place, that little piece, yes, and we'll take it away. All right, so that's basically subtracting that little piece inside. Are you with me? Okay, since they're the same bounds, we'll just keep it all in one. Keep it in the fam. Okay, don't worry about actually doing it. We've had enough practice integrating.
Beautiful.
Okay, but that's how we would set up this one. All good? Questions? The last one, 3 cosine theta. That's a circle on the x-axis. I know. 1 plus cosine theta. Okay, cosine of 0 is 1. 1 plus 1 is 2. 1 plus 0 is 1. 1 plus -1 is 0. 1 plus 0 is 1. Okay. This is a cardioid, yes. Okay. Now, we want the common interior. That's this part where it's common to both of them. Drawing polars is an art. Okay. So we want this thing. Now, be careful, guys, because we're going to draw a line out to our intersection, then a line out to our intersection. Okay. All right. Calculate our intersection. 3 cosine theta equals 1 plus cosine theta. For 2 cosine theta equals 1. Cosine is 1/2 when theta equals. Okay. Uh-oh. there's a tricky thing, guys. What's the equation of that cardioid?
1 plus cosine.
Okay, so if I go from, what do we say it was at? Pi over 3 to 5 pi over 3. I'm finding the wrong half of it.
We go negative 5
Yeah, so we're going to go from
negative 5.
negative pi over 3 to pi over 3. Okay? That will get us the part that we want.
So did you just switch the bounds from instead of pi over 3, 5 pi over 3 to 5 pi over 3, pi over 3?
You could go, no, you could go,
Go to 7.
sorry. I can't get it. You could go from there, but if you went, you can't go to pi over 3 because you can't go backwards from, like we can't. This is 2 pi. You could go from 5 pi over 3 to 7 pi over 3. Yes. Also, you could go from 0 to pi over 3 and then double it. What would you prefer?
Isn't there still area in the negative pi?
Yes, yes, yes. We'll get to that in a minute. We're going to go, what do you want to do?
Negative pi over 3.
Okay. So we'll go negative pi over 3 to pi over 3.
How would we identify that though when we're doing calculating like that?
It always will look like, because cosine always starts at 0 here. So, like, it's always going to go this way as it graphs. Anyways, as you plot the points, you know how it's going to go as you move
Oh,
on.
because we know we start from there.
Right, because you know when you plug 0 degrees in, you start here, and then the next point you plot is here, and then the next point you plot is here. So as you're going along, you know.
But if we're going from pi over 3 to 5 pi over 3, we would recognize that we're getting the exact opposite.
No, wait, maybe not.
Right. Okay. So,
And calculate the entire cardioid and then I just like left and right.
no.
No, but minus the pi over 3
To 5 pi over 3 part? Yeah, but that's extra work.
I think we just
extra work.
set up in those.
It's simpler to think about though.
It's just all
Well, you do you. It's all right. But, as long as, you know, there's like a ton of ways. That's the thing with polars, there's a ton of ways to do them. And they're like, they could all be right. Because the r's and thetas, there's a million ways to write the r's and thetas.
So are they really going to check our work all the time if we use like some really obscure R theta thing?
They'll look, they'll make sure that that it's right.
We can't just make them like be like as to
You know what? Usually they restrict you specifically to like the first quadrant or second quadrant or third quadrant. Anyways, Adine said, hey, this is only finding this part, right? Not these little, I call them almond slivers on the side.
Wait, are you just gonna find the area of the? No way. No.
Okay, so that only finds those parts. So when you're shading and you're missing parts, then you have to let me change it to the other equation. What's the other equation? 3 cosine theta. Okay, so I've got to find, we're going to start at 60. I've got to find the little extra part that cosine theta has. So we're going to go 60 to 90 to get that little piece, right? And then I'll double it. Or you can go 60 to 5 pi over 3 if you want to, you know. and then not double it. But I like to just go bless you.
That's what I'm saying, just calculate the entire cardio.
But you still have to calculate the circles parts. Because the part that we just calculated has nothing to do with the cardioid. Yeah. Okay. So this is like the almond sliver. Have you ever had almond slivers? Do you know what I'm talking about?
Just all into the half.
They do. They look like almond slivers. I'll show you what an almond sliver looks like. See? That's what a slivered almond looks like.
Oh, I was thinking about
Nuts.com verifies. That's exactly what that little piece looks like. Oh, almond, hiya. Need help finding your perfect almond treat? I'm here to help. No, I've found it. Oh, Benjamin. Thank you. Deborah from West Palm Beach
I was born there.
was very helpful. Okay. That's Deborah from West Palm Beach, right here. Okay.
Yeah,
This is a great deal. Rate this chat.
You gotta give like a 0.
Chat rated good. Thanks, Benjamin.
Send him a heart.
Hope you had a great Valentine's.
Send him a Modicon heart.
R equals
Copy paste.
no, I'm not gonna copy paste to theta. Oh, Benjamin left the chat. I gotta re-rate him.
You're welcome.
Thumbs down.
Ask him why you left.
Chat rated bad now. Benjamin. Jerk. Okay. Anyways,
Just ask him if he would be a Valentine.
I should have. Too bad.
He left the chat.
Left me to my own nut devices.
27 Valentine.
How
Okay.
will you ever pick out that though?
I don't know.
25.
Deborah from West Palm.
Okay. Try this thing. Try this last question. And then we're done. Benjamin. I know. I'll show you what the graph looks like of this. 2 plus sine 2 theta. I'll just show you. Yeah. No, because it's plus.
If it was multiplied, then it would be
2 plus, what is it? 2 plus what? Sine. There.
Oh my gosh, that's not
Well, it's not just a limaçon, because limaçons intersect at the origin. This is a peanut Oh, Benjamin, I needed you.
Go back.
When I really, you weren't there when I really needed you.
Do that.
So what are we integrating from? 0 to
0 to pi.
0 to pi. Okay.
Yo, what?
So we're finding that area.
Shouldn't it have been a
Okay. No, because it's
Oh, no, 'cause
2
it's not
theta.
Right.
Yeah.
Oh, you're weird.
I'm going on notes.com.
Okay. Try this last one, then we'll be done.
I don't think that's 0 to
Doesn't have to be perfect. Your drawing.
Yeah.
Area from 0 to 5.
Almond, no.
This is just a piece of
This is
slice.
just, I don't know, I'm lost without
This
this.
is
Can we have the integral? Can we just like write the integral and like that be it? Can we just like write the integral and that be it? We have to
I think my sketch is high quality. I thought the best sketch.
Yeah?
Yeah.
You can use your calculator to integrate, guys. Don't do it by hand. Just set it up by hand, and then use your calculator to integrate.
If I just write the door in.
Yeah, that's perfect. You can use your calculator to integrate this.
Do I want to do that? Well, first,
Yeah. No, don't put it in polar mode. Just use X and rectangular mode. Because polar mode doesn't allow you to find intersections or do anything else. So, yeah. Yeah.
use R.
But if you should do it so that you can make sure your buffer is right.
Wait, but if you
Or
do it in
fine.
polar form,
I mean, I'm not gonna know either way.
can't you integrate it in polar form though? Wouldn't that be better?
No. It's the same. And it's better to just keep it in rectangular for the whole.
So these all have the exact same values. It's just
Yeah.
Wait, this is a calculator.
Your X is your theta and your R is your Y. But you'll get like X theta and Y. You just have to know that there are and the rectangular, basically the rectangular wraps it this way, and the polar like wraps it back into a full circle.
Oh, so that means we have to like change it from polar to.
Wait, is it? Would this just be a calculated file where you can solve that?
Yes.
Okay.
A particle is
Yeah.
traveling
And you
along
just
a
go
particular
y1,
curve.
y2,
No.
and
No.
what's wrong?
I just looked at this problem and I started hurting. I thought all the math I need to do. I'm literally switching in R to X.
How did you D?
Yes.
How do you do D?
How do you do D?
Yes.
You find theta to t. Oh, that's already 5.
This is like the end of that.
So this is dx dt, so you take the derivative, plug it in, take the derivative of this with respect to time.
Fourth quarter was parametrics.
So and the meaning would be as theta is increasing.
No, as t is increasing, theta is
second part.
or sorry, as t is increasing,
quarter was my
you're
best last
moving
year.
right or left.
Huh? What was my best?
As theta, yeah, as theta is, when theta equals pi over 6, you are perfect.
Yeah.
No, I got so.
Okay, I don't think we have time to finish this problem. So, what I'm gonna do is, I'm going to,